In this video, we're going to begin Chapter 8, where we're going to look at rotational kinematics. You should recognize that word kinematics from the very first unit we covered when we studied motion. Well, all of that motion was linear kinematics. Now we're going to look at rotational kinematics. So the objects are going to be rotating, not just moving translationally. The simplest form of rotation is a rigid object that moves in circular paths around an axis of rotation. So if you picture a figure skater that's spinning and we have an axis of rotation that goes through the center of the person, if we pick any point on that person, we see that it is moving in a circular path around the axis of rotation. If we examine points A, B, and C, we see that they are all moving in circular paths. Paths of different radii, mind you, but they are all circular paths about the same axis of rotation. When we talk about translational kinematics, we have this idea of displacement being a linear distance that we travel. Well, in rotation, we may not be moving translationally. However, there is a displacement. And we call that displacement a angular displacement, which is a displacement of an angle. Oftentimes you may hear someone refer to something rotating 90 degrees or rotating 360 degrees because it's making a full circle. Well, we're going to use the same idea, except we're not going to use degrees. We are going to use radians to describe our angular displacement. And we typically measure these radians from the positive x-axis in the counterclockwise direction. So just like you first learned about opening up angles in Algebra 2 and pre-calc, opening from the positive x direction is the positive angular displacement direction. The formal definition of angular displacement is when a rigid body rotates about a fixed axis, the angular displacement is the angle swept out by a line passing through any point on the body and intersecting the axis of rotation perpendicularly. And as mentioned before, the typical convention is that the positive is the counterclockwise direction and the SI unit is in radians. So we're going to have to refer back to something we learned in geometry about the arc length and the radius and how they compare. And we know that the angle that is displaced in a circle is going to equal the ratio of the arc length to the radius. And so this is why we have a full 2 pi radians in a circle, because the circumference of a circle is 2 pi r, and we divide that by r, and so we're left with 2 pi radians. So this tells us that a full 360 degrees is in fact 2 pi radians. So if you're ever wondering why we have that as 2 pi, well, it tells you right there, because the angle is defined as the ratio of the arc length to the radius. Let's look at an example here of a satellite that's moving in a circular path about the Earth. So we have two satellites that are put into the same circular orbit in that their radius is 4.23 times 10 to the 7th meters. And I'm sorry for the formatting error. This should be 10 to the 7th. Sometimes when I convert over onto the iPad, it screws up. So anyway, that is 10 to the 7th, not 107 meters. And so that's the radius of the circular orbit. And if the angular separation of the two satellites is 2 degrees, we want to find the arc length that separates them. So let's make sure we understand what we're talking about here. We're not necessarily talking about the exact distance or the shortest distance between the two. We want to talk about the path distance, so the distance along the circular path that differs between their two positions. So in order to do this, we need to look at the angle, knowing that it's going to be the ratio of the arc length to the radius. But first things first, we do need to convert. We are given an angle in degrees, so we convert to radians by multiplying by pi over 180 or 2 pi over 360 to get an angle of 0.0349 radians. And then we can use that equation to find the arc length to be the radius times the angle, so we get 4.23 times 10 to the 7th meters times that angle in radians, and we get about 1.5 million meters, or around 920 miles. Now remember, this doesn't tell us that the two satellites are 920 miles apart. They have an arc length between them of 920 miles. So this satellite here will have to travel 920 miles along its circular path to get to the position of that satellite. Let's look at a conceptual example here. And talking about the diameter of the sun is about 400 times greater than that of the moon. And by coincidence, the sun is also about 400 times farther from the Earth than the moon. So we want to use this information to tell that for an observer on Earth, how does the angle subtended by the moon compare with the angle subtended by the sun, and explain why this result leads to a total solar eclipse. So let's picture first this person we have here on Earth, and they can look at the sun, and what we're talking about, this angle here, is the angle that we see between the bottom of the sun and the top of the sun. And we see an angle for both the moon and the sun, and we want to see how those two angles compare. So let's look at these separately, and let's talk about the angle in radians. We know that that's going to equal the arc length divided by the radius. This arc length of the sun is approximately the diameter of the sun. Now, it's not perfect because it really is curved here a little bit, but because we're looking at such a small angle and such a really big sun, we can say the diameter of the sun is pretty darn close to that arc length right there at the end of our angle. We can use the same reasoning for the moon and say that the arc length at the end of the angle that we're seeing with the moon is going to be the diameter of the moon. Now, we're told that the diameter of the sun is 400 times greater than the diameter of the moon. So that means that the arc length of the sun is going to be 400 times greater than the arc length of the moon. Well, if we want to look at the angle and look at the radius, so the radius here is going to be the distance between the observer and the moon, and the distance between the observer and the sun, then we're also told that the radius of the sun is equal to 400 times that of the radius of the moon. So looking at these ratios, by taking the arc length of the sun divided by the radius of the sun, we get the arc length of the moon divided by the radius of the moon. So the theta for the sun is equal to the arc length of the moon divided by the radius of the moon, which also is the angle for the moon. And this reason alone is the reason why we can have a total solar eclipse, only because the angle of the moon is equal to the angle of the sun. And so when the moon is in between the sun and the observer, those angles overlap, and that's why the moon can totally blot out the sun, because their angles are the same, and so we can't see the sun. Now, what actually happens? We see a tiny little ring of the sun peek through, because we said before, these 400s, those are approximate, so the angles aren't perfect, but they're pretty darn close. So that's why we just see that tiny little ring in the solar eclipse, because the angles are so close that the moon, even though it's so much smaller, it's also so much closer, it can block out the sun. We're going to talk more about this angular displacement and rotation in general in class. It may help if you read the section out of the book before coming to class and come prepared with any possible questions that you may have. Thanks for watching.